Hey guys, welcome to this new story. Today, we turn our eyes toward our closest neighbor in space and a place that has sparked mystery for generations, the far side of the moon. From Earth, we always see the same familiar face of the moon shining in the night sky. But the other half, hidden from view, remained unknown to humanity for thousands of years. It wasn't until spacecraft finally traveled around the moon that we discovered what truly lies there. The far side is not smooth and bright like the side we know. Instead, it is covered with countless craters, ancient scars left by billions of years of impacts. Huge basins stretch across its surface, mountains rise from shattered ground, and dark plains are far less common than on the side facing Earth. Why are the two sides of the moon so different? What shaped this hidden half in such a strange way? Beneath its dusty surface lies a long history of violent collisions, deep internal forces, and clues about the early days of our solar system. In this video, we travel to the far side of the moon to uncover what really exists there and what this hidden world reveals about the story of our cosmic neighbor. Above Earth, at an average distance of about 384,000 kilometers, the moon moves through space in a slow and steady path. It circles Earth once every 27 days. During that time, the moon also turns once around its own axis. The two motions happen at the same rate. Because of this balance, the same side of the moon always faces Earth. From the ground on Earth, this pattern is easy to see over time. The moon changes shape across the month. It grows from a thin crescent to a full bright disk, then slowly shrinks again. But even as its shape changes, the markings on its surface remain almost the same. The same dark plains and bright highlands appear again and again. Those features never move out of view. For thousands of years, people across the world looked up and saw the same face of the moon. No matter where someone stood on Earth, the visible side remained familiar. The dark shapes that form the lunar Maria, the lighter areas filled with craters, and the bright rays from old impacts stayed in the same places. Because of this constant view, early observers believed the entire moon looked like the part they could see. Telescopes revealed more detail after the early 1600s, but they did not change this basic limitation. Even the most powerful telescopes on Earth could only show the half of the moon that faced our planet. The other half remained hidden. This unseen half slowly became known as the far side of the moon. It is sometimes called the dark side, but this name can be misleading. The far side is not always dark. It receives sunlight just like the near side. Day and night still pass across it as the moon turns. The reason it stayed unseen is not darkness. The reason is motion. The moon is held in a special balance with Earth. Over long periods of time, gravity between the two bodies shaped how the moon rotates. Early in the moon's history, it likely spun faster, but the pull of Earth created small changes inside the moon's interior. These changes slowly removed energy from the moon's spin. This process continued for millions of years. Little by little, the moon's rotation slowed. Eventually, it reached a stable point where one full rotation took exactly the same time as one orbit around Earth. When this balance formed, the moon became locked into its present motion, and one hemisphere now faces Earth at all times, while the opposite hemisphere faces away. Scientists describe this condition as tidal locking. The effect can be explained through simple motion. Imagine a body moving in a circle around another object, while also turning once during that trip. If the timing of the turn matches the orbit, the same side will always face inward. The opposite side will always face outward. This is what happens between Earth and the moon. Because of tidal locking, observers on Earth can only see about 59% of the moon's surface over time. Small shifts in the moon's position allow a slight change in viewing angle. These movements are called librations. They tilt the moon slightly from side to side or up and down. Even with librations, the majority of the far side remains hidden from direct view. For most of human history, no one knew what existed there. The moon itself formed long before humans appeared on Earth. Current scientific models suggest it formed around 4.5 billion years ago. The leading explanation involves a large collision between early Earth and another body roughly the size of Mars. After this impact, debris entered orbit around Earth. Over time, that material gathered together through gravity and formed the moon. During its early years, the young moon was extremely hot. Much of its outer layer was covered by molten rock. As this material cooled, it formed a solid crust. Beneath the crust, parts of the interior remained warm for a long time. While the moon cooled and changed, it also began the slow process that led to tidal locking. Earth's gravity pulled more strongly on the near side of the moon than on the far side. This uneven pull created small stretching forces inside the lunar body. These forces produced friction within the moon's interior layers. The friction slowly reduced the moon's original spin. Over a long period, the moon settled into the stable rotation that exists today. Once this balance formed, the hidden hemisphere remained turned away from Earth. From that moment forward, the far side became a region no human eye could see from the ground. Ancient sky watchers had no way to confirm what existed there. Even after the invention of telescopes, the limitation remained the same. Telescopes improved the clarity of the near side. Craters became visible. Mountain chains appeared. Dark plains showed their shapes more clearly. But the far side stayed beyond reach. Maps of the moon produced during the 1600s and 1700s reflected this limit. Early lunar maps showed only the visible hemisphere. Astronomers carefully recorded every crater, ridge, and plain they could observe. These maps became more detailed over time. Still, half of the moon remained blank. In some maps, the edge of the visible surface was marked clearly, and the rest was left empty. There was no reliable information about what lay beyond that line. This gap in knowledge lasted for centuries. Even as science advanced and telescopes improved, the far side stayed hidden. Light from that hemisphere never traveled directly toward Earth. Mountains, valleys, and craters on that side remained unknown. Only the motion of the moon gave a clue that another half existed. From a simple physical point of view, the moon must have a complete sphere. The unseen half had to contain landforms just like the near side, but no one could confirm their shape or arrangement. Many people wondered if the far side looked the same as the visible side. The near side shows large dark plains called Maria. These wide areas formed long ago when molten rock flowed across the surface and cooled into smooth basalt. Because these plains appear darker than the surrounding highlands, they stand out clearly when the moon is full. For centuries, observers assumed these dark plains might cover the entire moon. But without direct images, this idea could not be tested. The far side remained one of the largest unknown regions close to Earth. During the 19th century, scientists began to study the moon more carefully. Photography allowed more accurate records of the visible surface. Lunar photographs revealed fine details of crater walls, central peaks, and long rays of bright material spreading across the ground. Even with these new tools, the same limitation remained. Cameras on Earth could only capture the near side. At that time, reaching the far side seemed impossible. The moon's distance made travel extremely difficult. Rockets capable of leaving Earth did not yet exist. The idea of sending machines around the moon belonged more to imagination than to engineering, so the hidden hemisphere remained beyond observation. Despite this limit, scientists continued to study the motion that kept the moon locked toward Earth. Careful measurements of the moon's orbit helped explain how tidal locking formed and why it remained stable. Earth's gravity continues to hold the moon in this pattern today. The pull between the two bodies is strong enough to maintain the same orientation during each orbit. As the moon travels around Earth, its near side always faces inward. At the same time, the far side always points outward into space. And this means that someone standing on the far side would never see Earth in the sky. The Earth would remain permanently below the horizon. From that distant surface, the sky would look different from the one seen from the near side. But for most of human history, this view existed only as a scientific idea. No person or instrument had yet reached the far side. The hidden hemisphere remained a place defined only by physics and motion. Its existence was certain, its surface, however, remained unknown. This situation lasted until the middle of the 20th century. Only then did technology develop far enough to send spacecraft beyond Earth's atmosphere and toward the moon. For the first time, machines would travel around the moon and reveal the surface that had remained unseen for billions of years. Before those missions began, however, one fact had already become clear through science. The far side of the moon was not hidden because of darkness. It was hidden because the moon and Earth moved together in a stable, locked rhythm that formed long ago and continues today. Above Earth, at an average distance of about 384,000 kilometers, the moon moves through space in a slow and steady path. It circles Earth once every 27 days. During that time, the moon also turns once around its own axis. The two motions happen at the same rate. Because of this balance, the same side of the moon always faces Earth. From the ground on Earth, this pattern is easy to see over time. The moon changes shape across the month. It grows from a thin crescent to a full bright disk, then slowly shrinks again. But even as its shape changes, the markings on its surface remain almost the same. The same dark plains and bright highlands appear again and again. These features never move out of view. For thousands of years, people across the world looked up and saw the same face of the moon. No matter where someone stood on Earth, the visible side remained familiar. The dark shapes that form the lunar Maria, the lighter areas filled with craters, and the bright rays from old impacts stayed in the same places. Because of this constant view, early observers believed the entire moon looked like the part they could see. Telescopes revealed more detail after the early 1600s, but they did not change this basic limitation. Even the most powerful telescopes on Earth could only show the half of the moon that faced our planet. The other half remained hidden. This unseen half slowly became known as the far side of the moon. It is sometimes called the dark side, but this name can be misleading. The far side is not always dark. It receives sunlight, just like the near side. Day and night still pass across it as the moon turns. The reason it stayed unseen is not darkness. The reason is motion. The moon is held in a special balance with Earth. Over long periods of time, gravity between the two bodies shaped how the moon rotates. Early in the moon's history, it likely spun faster. But the pull of Earth created small changes inside the moon's interior. These changes slowly removed energy from the moon's spin. This process continued for millions of years. Little by little, the moon's rotation slowed. Eventually, it reached a stable point, where one full rotation took exactly the same time as one orbit around Earth. When this balance formed, the moon became locked into its present motion. One hemisphere now faces Earth at all times, while the opposite hemisphere faces away. Scientists describe this condition as tidal locking. The effect can be explained through simple motion. Imagine a body moving in a circle around another object, while also turning once during that trip. If the timing of the turn matches the orbit, the same side will always face inward. The opposite side will always face outward. This is what happens between Earth and the moon. Because of tidal locking, observers on Earth can only see about 59% of the moon's surface over time. Small shifts in the moon's position allow a slight change in viewing angle. These movements are called librations. They tilt the moon slightly from side to side or up and down. Even with librations, the majority of the far side remains hidden from direct view. For most of human history, no one knew what existed there. The moon itself formed long before humans appeared on Earth. Current scientific models suggest it formed around 4.5 billion years ago. The leading explanation involves a large collision between early Earth and another body roughly the size of Mars. After this impact, debris entered orbit around Earth. Over time, that material gathered together through gravity and formed the moon. During its early years, the young moon was extremely hot. Much of its outer layer was covered by molten rock. As this material cooled, it formed a solid crust. Beneath the crust, parts of the interior remained warm for a long time. While the moon cooled and changed, it also began the slow process that led to tidal locking. Earth's gravity pulled more strongly on the near side of the moon than on the far side. This uneven pull created small, stretching forces inside the lunar body. These forces produced friction within the moon's interior layers. The friction slowly reduced the moon's original spin. Over a long period, the moon settled into the stable rotation that exists today. Once this balance formed, the hidden hemisphere remained turned away from Earth. From that moment forward, the far side became a region no human eye could see from the ground. Ancient sky watchers had no way to confirm what existed there. Even after the invention of telescopes, the limitation remained the same. Telescopes improved the clarity of the near side. Craters became visible, mountain chains appeared, dark plains showed their shapes more clearly, but the far side stayed beyond reach. Maps of the moon produced during the 1600s and 1700s reflected this limit. Early lunar maps showed only the visible hemisphere. Astronomers carefully recorded every crater, ridge, and plain they could observe. These maps became more detailed over time. Still, half of the moon remained blank. In some maps, the edge of the visible surface was marked clearly, and the rest was left empty. There was no reliable information about what lay beyond that line. This gap in knowledge lasted for centuries. Even as science advanced and telescopes improved, the far side stayed hidden. Light from that hemisphere never traveled directly toward Earth. Mountains, valleys, and craters on that side remained unknown. Only the motion of the moon gave a clue that another half existed. From a simple physical point of view, the moon must have a complete sphere. The unseen half had to contain landforms, just like the near side. But no one could confirm their shape or arrangement. Many people wondered if the far side looked the same as the visible side. The near side shows large, dark plains, called Maria. These wide areas formed long ago when molten rock flowed across the surface and cooled into smooth basalt. Because these plains appear darker than the surrounding highlands, they stand out clearly when the moon is full. For centuries, observers assumed these dark plains might cover the entire moon, but without direct images, this idea could not be tested. The far side remained one of the largest unknown regions close to Earth. During the 19th century, scientists began to study the moon more carefully. Photography allowed more accurate records of the visible surface. Lunar photographs revealed fine details of crater walls, central peaks, and long rays of bright material spreading across the ground. Even with these new tools, the same limitation remained. Cameras on Earth could only capture the near side. At that time, reaching the far side seemed impossible. The moon's distance made travel extremely difficult. Rockets capable of leaving Earth did not yet exist. The idea of sending machines around the moon belonged more to imagination than to engineering. So the hidden hemisphere remained beyond observation. Despite this limit, scientists continued to study the motion that kept the moon locked toward Earth. Careful measurements of the moon's orbit helped explain how tidal locking formed and why it remained stable. Earth's gravity continues to hold the moon in this pattern today. The pull between the two bodies is strong enough to maintain the same orientation during each orbit. As the moon travels around Earth, its near side always faces inward. At the same time, the far side always points outward into space. This means that someone standing on the far side would never see Earth in the sky. The Earth would remain permanently below the horizon. From that distant surface, the sky would look different from the one seen from the near side. But for most of human history, this view existed only as a scientific idea. No person or instrument had yet reached the far side. The hidden hemisphere remained a place defined only by physics and motion. Its existence was certain. Its surface, however, remained unknown. This situation lasted until the middle of the 20th century. Only then did technology develop far enough to send spacecraft beyond Earth's atmosphere and toward the moon. For the first time, machines would travel around the moon and reveal the surface that had remained unseen for billions of years. Before those missions began, however, one fact had already become clear through science. The far side of the moon was not hidden because of darkness. It was hidden because the moon and Earth moved together in a stable, locked rhythm that formed long ago and continues today. As more images of the far side arrived in the years after the first photographs, the overall pattern of the surface became clearer. The early pictures from the first mission had shown a rough outline. Later missions added sharper views and wider coverage. Piece by piece, the hidden hemisphere of the moon became easier to understand. The most noticeable feature was the number of craters. On the near side of the moon, large dark plains break up the surface. These plains appear smooth from a distance. When the moon is full, they form the familiar shapes that people have recognized for centuries. Many cultures imagined patterns in them. Some saw faces, animals, or figures in the sky. These dark regions are called Maria. The word comes from Latin and means seas. Early astronomers believed these smooth areas might contain water. Later studies showed they are not seas at all. They are wide plains of hardened volcanic rock. When scientists looked at the far side images, they noticed something very different. The Maria were mostly missing. Instead of broad, dark plains, the far side was covered almost entirely by brighter, rougher terrain. The surface looked crowded with circular impact marks. Craters of many sizes overlapped each other. Some craters were only a few kilometers wide. Others stretched for hundreds of kilometers. Their edges formed rings of broken rock that rose above the surrounding ground. The land between these craters was uneven and elevated. This region is called the lunar highlands. The highlands are made of older rock. They formed early in the moon's history when its outer layer cooled and hardened. These rocks are lighter in color than the basalt found in the Maria. Because of this difference in material, the far side reflects more sunlight. When viewed from spacecraft, the surface often appears brighter overall than many areas of the near side. The number of craters also reveals something about the age of the surface. In general, older areas of the moon have more craters. Over billions of years, objects from space strike the surface again and again. Each impact leaves a mark. If a region remains unchanged for a very long time, the number of craters increases. On the far side, the high crater density suggests that much of the surface has remained in place for extremely long periods. The near side shows a different pattern. In many places, older craters were covered long ago by flows of molten rock. These flows filled large basins and spread outward, forming the dark plains seen today. Because these volcanic flows covered older impacts, they reduced the number of visible craters in those regions. The far side did not experience the same level of volcanic flooding. As a result, its ancient surface remained exposed. This contrast between the two hemispheres is one of the most striking features of the moon. When scientists compare maps of both sides, the difference becomes clear even from a simple view. The near side contains many large Maria, while the far side contains very few. One reason for this difference involves the thickness of the moon's crust. Measurements from spacecraft show that the crust on the far side is thicker than the crust on the near side. A thicker crust makes it harder for molten rock from below to reach the surface. Long ago, when the moon's interior was warmer, molten material could rise toward the surface through cracks and weak areas. On the near side, the thinner crust allowed this rock to spread across large basins. On the far side, the thicker crust acted as a stronger barrier. Molten rock had more difficulty reaching the surface there. Because of this, large volcanic plains formed mainly on the near side. The far side still contains a few smaller maria, but they cover only a small fraction of the surface compared with the near side. Another difference appears in the shape of the terrain. The far side contains long chains of overlapping craters and basins. Many of these features formed when large objects struck the moon early in its history. The force of these impacts created wide circular structures. Some basins are surrounded by rings of mountains created during the impact event. These rings formed as the ground rose and collapsed during the violent collision. Over time, smaller impacts struck inside these basins, creating layers of younger craters within older ones. This process produced a complex pattern of circles within circles across the surface. The near side also contains impact basins, but many were later filled by volcanic rock. This filling smoothed their floors and reduced the number of visible crater walls. On the far side, the basin floors often remain rough and uneven. Large ridges and broken blocks of rock stand where the ground once lifted and fell during ancient impacts. Another feature common on the far side is the presence of secondary craters. When a large impact occurs, it throws debris high above the surface. Some of this material travels long distances before falling back down. When it lands, it can create smaller craters. These secondary craters often appear in chains or clusters. Because the far side has experienced less volcanic resurfacing, many of these secondary craters remain visible today. This adds to the crowded appearance of the terrain. The slopes of many far side craters show signs of gradual change over time. Small landslides occur when loose material shifts down steep walls. Tiny impacts could also break apart rock and produce dust. This layer of loose material is called regolith. Regolith covers nearly the entire lunar surface. It forms slowly as impacts break solid rock into smaller pieces. On the far side, the regolith layer can be quite deep in some areas. Over long periods, and countless impacts have mixed and crushed the surface rock. The result is a thick blanket of fine dust and broken fragments. When spacecraft cameras capture images of the far side, sunlight highlights the sharp edges of crater rims and mountain peaks. Shadows fall across crater floors, showing their depth and shape. Some craters have central peaks rising from the middle. These peaks formed during the impact process. After the initial explosion, the ground rebounded upward before settling again. This rebound created a small mountain in the center of the crater. Such features are common across both sides of the moon, but they appear especially clear in the far side highlands. The large number of craters means that many older impacts have been partly damaged by later ones. A new impact can strike the rim of an older crater or cut across its floor. Over time, the surface becomes a record of overlapping events. By studying these patterns, scientists can estimate the relative age of different areas. Regions with many overlapping craters are usually older than regions with fewer. The far side shows some of the oldest exposed surfaces on the moon. This makes it an important place for studying the early history of the solar system. The shape of the terrain also affects how sunlight spreads across the ground. High crater rims and mountain ridges cast long shadows when the sun is low. These shadows can remain for long periods near the lunar poles. In lower areas, sunlight reaches the surface more directly. The changing angle of light across the moon during its long day reveals small details in the landscape. Each lunar day lasts about 29 Earth days, from sunrise to sunrise. During this time, sunlight slowly moves across the surface. The far side experiences the same cycle of day and night as the near side. Half of the time it is lit by the sun, and half of the time it lies in darkness. Despite this shared cycle, the terrain remains very different. Wide volcanic plains shape the appearance of the near side. Cratered highlands dominate the far side. The contrast between these two surfaces became clearer as more spacecraft images arrived. Each mission improved the maps created from the earliest photographs. High resolution cameras revealed smaller craters, narrow valleys, and ridges hidden in earlier images. Scientists began to see the far side not just as a rough region, but as a detailed landscape with many distinct structures. Large impact basins, mountain chains, and fields of overlapping craters formed a complex map of ancient events. These patterns told a story about the moon's early past. The far side had preserved much of its original surface, while the near side had been reshaped by volcanic activity. Together, the two hemispheres showed how different processes could shape a single world. The hidden half of the moon was no longer unknown. It had become a landscape that scientists could measure, compare, and study in detail. Across the far side of the moon, nearly every stretch of ground shows signs of past impacts. The surface acts like a long record of collisions that happened over billions of years. Each crater marks the place where a rock from space struck the moon at heat speed. Most of these objects were small. Some were only a few meters wide. Others were much larger, measuring several kilometers across. When they struck the moon, they carried enormous energy. Even a small rock moving through space can travel faster than 20 kilometers per second. At that speed, the impact releases energy in a sudden burst. The ground at the point of contact breaks apart and spreads outward. Rock turns into fragments and dust. The force pushes material away from the center of the impact, forming a round crater with raised edges. Because the moon has almost no air, these impacts happen without slowing down. On Earth, many incoming objects burn or break apart in the atmosphere before reaching the ground. The moon has no such protection. As a result, the surface receives the full force of these collisions. Over time, each new impact leaves its own mark. Older craters are sometimes cut by newer ones. Small craters appear inside large basins. Some crater walls collapse inward as loose material slides down their slopes. These layers of damage build up slowly across the surface. On the far side of the moon, this pattern is especially clear. Many regions are filled with overlapping craters that stretch as far as the eye can see in spacecraft images. The ground appears rough and broken, shaped by repeated impacts. The reason for this long record is simple. Very little changes the surface after a crater forms. The moon has no wind and no flowing water. There are no oceans and no moving plates in the crust. Without these forces, the landscape changes very slowly. Craters can remain visible for billions of years. Only later impacts or slow landslides alter their shapes. Because of this, the far side preserves some of the oldest surfaces in the solar system. Scientists study these craters carefully. By counting how many appear in a given area, they can estimate how long that surface has been exposed. Regions with many craters usually formed earlier than regions with fewer. This method helps researchers build a timeline for the moon's past. The earliest period in lunar history saw the highest number of impacts. During that time, many leftover pieces of rock still moved through the young solar system. These objects struck planets, moons, and other bodies frequently. The moon records much of this early activity. One of the largest results of these ancient collisions is the formation of giant impact basins. These basins are far larger than ordinary craters. Some stretch hundreds or even thousands of kilometers across. When an object large enough strikes the surface, the ground reacts in a complex way. First, the impact blasts a deep hole into the crust. Then the walls collapse inward. The floor rises slightly before settling again. Rings of mountains form around the edge of the basin as the ground shifts during the event. The final structure can include several circular rings, each marking a stage in the collapse of the surface. One of the most important examples lies on the far side of the moon. This structure is known as the South Pole Aitken Basin. It extends across a large portion of the southern hemisphere of the far side. From edge to edge, the basin measures roughly 2,500 kilometers in diameter. That distance is greater than the width of many large countries on Earth. Its depth also stands out. Parts of the basin floor lie several kilometers below the surrounding terrain. The event that created it was one of the largest known impacts in the solar system. Scientists believe the collision happened more than 4 billion years ago. At that time, the moon was still young. Its outer layers had cooled, but the interior remained warmer than it is today. When the massive object struck, the force penetrated deep into the crust. Some researchers think the impact may have exposed material from the moon's deeper layers. Because of this possibility, the basin is an important area for scientific study. Samples from its surface could reveal information about the structure of the moon's interior. The shape of the basin is not perfectly circular today. Over billions of years, smaller impacts have altered its edges. Craters formed inside the basin and partly covered the original surface. Still, the overall outline remains visible in spacecraft maps. Large sections of the far side terrain lie within or near this giant structure. The ground inside the basin contains many craters, but the Utah's surface is slightly smoother than some nearby highland regions. This difference hints that the basin floor may have been reshaped after the original impact. Some evidence suggests that molten rock once filled parts of the basin long ago. However, the amount of volcanic flooding there was much smaller than in the Maria on the near side. The thick crust on the far side likely limited how much molten rock could reach the surface. As a result, the basin remained mostly rough and heavily cratered. The presence of such a huge impact structure shows how violent the early solar system could be. Large objects once traveled through space in numbers far greater than today. Many eventually collided with planets and moons, leaving marks that still remain. The moon acts like a preserved record of this time. Because its surface changes slowly, the evidence of those ancient events can still be seen clearly. Beyond the giant basin, the far side contains many other impact features of different sizes. Some are only a few kilometers wide. Others form wide rings of mountains around large depressions. These features help scientists understand the energy involved in past collisions. The size of a crater depends on several factors. The speed of the incoming object plays an important role. So does its mass and the angle at which it strikes the surface. Even a moderate change in these conditions can alter the final shape of the crater. Impacts that arrive at a steep angle tend to produce nearly circular craters. Those that strike at shallow angles can create slightly stretched shapes. Debris from the explosion spreads outward from the center, forming rays and scattered fields of rock. On the far side, many craters still show these patterns. Bright streaks of material extend from some crater rims, marking the paths taken by ejected debris. These rays can stretch for hundreds of kilometers before fading into the surrounding terrain. Over time, micrometeorites slowly break down these features. Tiny impacts happen constantly across the lunar surface. Each one adds a small amount of dust and breaks apart existing rock. This gradual process softens the edges of older craters. Still, the main shapes remain visible for extremely long periods. The far side shows many stages of this slow change. Some craters appear sharp and well defined. Their rims stand high above the surrounding ground, and their central peaks remain clear. These craters formed more recently in lunar history. Others appear worn and partly filled with debris. Their walls have collapsed inward, and their floors contain smaller craters. These older structures have endured countless smaller impacts since their formation. When scientists compare the far side to the near side, the difference in crater density stands out again. Large sections of the near side were resurfaced by volcanic flows long after the earliest impacts occurred. Those flows buried many older craters. The far side did not experience the same level of volcanic activity. Because of this, the record of early impacts remains much more complete there. Studying this record helps scientists understand the conditions that existed in the young solar system. The pattern of impacts across the moon provides clues about how many objects once traveled through nearby space. It also helps researchers compare the history of other bodies, including Earth. On Earth, most evidence from that early time has disappeared. Plate movement, erosion, and weather have removed many ancient impact marks. The Moon, by contrast, still holds much of that record. The far side, with its dense fields of craters and giant basins, preserves one of the clearest views of that distant era. Each crater marks a moment when a piece of rock from space met the lunar surface at great speed. Together, these impacts shaped the landscape seen today. They also created the long chain of features that scientists now study to learn how the moon and the solar system formed long ago. When scientists compared the two halves of the moon in greater detail, the question became clear. Why does one side show wide, dark plains, while the other side shows mostly bright and rough highlands? The answer lies deep inside the moon and in the way heat moved through its interior long ago. The dark plains on the near side formed from volcanic rock. Long after the moon first formed, parts of its interior remained very hot. Melted rock, called magma, existed beneath the surface. In certain places, this magma found paths upward. It moved through cracks in the crust and spread across the ground. When the molten rock cooled, it hardened into dark basalt. These flows filled large impact basins and formed the maria that are visible from Earth today. On the far side, this process happened far less often. The main reason involves the thickness of the moon's crust. Measurements taken by orbiting spacecraft show that the crust is not the same everywhere. On average, the crust on the far side is much thicker than the crust on the near side. In some places, the difference may reach tens of kilometers. A thicker crust creates a stronger barrier for rising magma. Magma moving upward from the interior must push through the solid rock above it. If the crust is thin, this path can open more easily. If the crust is thick, the pressure may not be strong enough to break through. This difference played an important role in shaping the two hemispheres. On the near side, the crust was thin enough in several places for magma to reach the surface. Large impacts had already created deep basins there. These basins weakened the crust even more. When molten rock rose from below, it spread across these basins and filled them. Over time, layer after layer of basalt formed the wide dark plains seen today. The far side followed a different path. There, the thicker crust prevented most magma from reaching the surface. Even when large impacts created basins, the rock above the interior remained difficult to break through. Because of this barrier, volcanic flooding happened rarely. The old highland terrain remained exposed instead of being covered by basalt flows. Another factor also helped create the difference between the two sides. Long ago, the moon may have had an uneven distribution of heat-producing elements in its crust and mantle. Certain elements release heat slowly over time as they change form. These elements include materials such as uranium and thorium. Studies of lunar rock samples and orbital measurements show that many of these heat-producing elements are concentrated more strongly on the near side. This region is sometimes called the Procellarum area by scientists. It covers a large portion of the near side where many maria exist. Because more heat remained in that part of the moon, magma stayed active there for longer periods. The extra heat helped keep the rock beneath the crust, partly, melted. Over time, this made volcanic eruptions more likely in those regions. On the far side, fewer of these elements were present. The interior cooled more quickly there. With less heat available, magma became less common and less mobile. The difference in internal heat helped reduce volcanic activity on that hemisphere. Gravity measurements from spacecraft also reveal differences in structure beneath the lunar surface. Some areas under the Maria contain dense layers of basalt. These heavy layers create slight increases in the moon's gravitational pull in those regions. Scientists call these features mass concentrations, or mascons. Mascons formed when thick basalt flows filled large impact basins. The heavy rock remained after the lava cooled, adding extra mass to the crust. Many strong mascons appear beneath Maria on the near side. The far side shows far fewer of these features. This pattern supports the idea that volcanic flooding occurred mainly on the hemisphere facing Earth. The large basins on the far side therefore remained mostly unchanged after the original impacts that formed them. Their floors stayed rough and cratered rather than smooth and dark. Over billions of years, new impacts continued to shape both sides of the moon. However, the earlier volcanic events had already created a clear contrast between the two hemispheres. When sunlight strikes the moon, this contrast becomes easy to see, even from Earth. The near side shows large dark shapes against lighter highlands. These dark areas mark the ancient lava plains. The far side, when viewed by spacecraft, appears brighter overall. Its surface is dominated by highland rock that reflects more light. The lack of large Maria there gives the landscape a more uniform appearance. This uneven distribution of volcanic plains remains one of the moon's most unusual features. Most planetary bodies do not show such a strong difference between two hemispheres. Researchers continue to study why the crust became thicker on the far side in the first place. One idea involves the way the young moon cooled after it formed. During its early history, the moon likely had a deep layer of molten rock near its surface. As this molten layer cooled, lighter minerals rose upward and formed the first crust. If the cooling process happened unevenly, some areas could have developed thicker crust than others. Another idea connects the difference to Earth itself. Because the moon has always faced the same side toward Earth after tidal locking formed, the near side remained slightly warmer during its early cooling period. Heat from the young Earth may have affected how the lunar crust formed. If the near side stayed warmer for longer, it may have slowed the formation of thick crust there. Meanwhile, the far side cooled faster and developed a stronger outer layer. Over time, this difference could have influenced where magma was able to reach the surface. These ideas are still being studied. Data from modern lunar missions continues to improve understanding of the moon's internal structure. Seismic measurements, gravity mapping, and surface chemistry all help scientists build a clearer model of the lunar interior. Even with these studies, the main result remains clear. The near side and far side of the moon followed different geological paths. One hemisphere developed wide volcanic plains. The other remained mostly highland terrain, marked by ancient impacts. Together they show how internal heat, crust thickness, and impact history combine to shape the surface of the moon. The far side preserved the early record of collisions. The near side reveals the power of volcanic activity that followed those impacts. Both processes are part of the long history written across the lunar surface. Among all the features on the far side of the moon, one region stands out because of its enormous size. This structure is known as the South Pole Aitken Basin. It stretches across the southern part of the far side and reaches close to the moon's south pole. The basin is one of the largest known impact structures in the entire solar system. From one edge to the other, it measures about 2,500 kilometers across. To understand this scale, it helps to compare it with large distances on Earth. The basin is wider than the distance between many major cities across continents. If placed on Earth, it would stretch across several countries. Its depth is also remarkable. The floor of the basin lies several kilometers below the surrounding terrain. Some of the lowest points on the moon are located inside this structure. The drop from the outer rim toward the basin floor reveals how powerful the original impact must have been. Scientists believe the basin formed more than 4 billion years ago. At that time, the solar system still contained many large pieces of rock left over from its formation. Some of these objects traveled through space on paths that crossed the moon's orbit. One of these objects eventually struck the moon with enormous force. The impact energy released during this event was far greater than that produced by smaller crater forming collisions. When the object struck the surface, it blasted through the crust and pushed material outward in every direction. The ground around the impact site broke apart and lifted upward. Large sections of rock moved outward and upward before collapsing again. This motion created rings of mountains that marked the edges of the basin. The shape of the South Pole Aitken Basin shows signs of this violent process. Although later impacts have changed parts of the surface, scientists can still trace the outline of the structure. The basin does not appear as a single simple crater. Instead, it forms a wide depression surrounded by rough highlands and broken rings of elevated terrain. The interior surface contains many younger craters that formed after the main impact. These later impacts partly cover the original basin floor. Still, the overall structure remains clear when viewed from orbit. Modern spacecraft have mapped the basin in great detail. Laser altimeters and radar instruments measure the height and depth of the surface. These measurements show how the terrain slopes downward from the outer rim toward the center. The deepest areas lie near the southern part of the basin. These low regions hold valuable clues about the moon's interior. The original impact may have pushed aside or removed a large portion of the crust. In some areas, material from deeper layers may have reached the surface. If this is true, the basin floor could contain rocks that formed far below the original crust, and such rocks would provide rare information about the structure of the moon's inner layers. Spacecraft instruments have detected differences in the chemical makeup of rocks within the basin. Some areas show signs of minerals that are less common in the lunar highlands. These materials may have come from the moon's mantle, the layer that lies beneath the crust. The mantle contains rock that formed during the moon's earliest cooling period. If pieces of that layer reach the surface during the basin forming impact, scientists may be able to study them directly. Understanding the mantle is important because it holds clues about how the moon formed and how its interior changed over time. The South Pole Aitken Basin may therefore act as a window into deeper parts of the moon. Gravity measurements also reveal unusual patterns across this region. When spacecraft pass above the basin, they detect small changes in the moon's gravitational pull. These variations occur because the density of rock beneath the surface is not the same everywhere. Some parts of the basin contain heavier rock than nearby areas. These differences help scientists estimate what lies beneath the surface layers. By combining gravity data with surface images, researchers can build models of the basin's structure. These models suggest that the original impact removed or displaced a large volume of crust. The event may have exposed deeper material before later impacts covered it with debris. The basin's age also makes it important. Because it formed very early in lunar history, it records conditions that existed not long after the moon itself formed. Studying such an ancient structure helps us scientists understand how common large impacts were during the early solar system. Many planets and moons experienced heavy bombardment during that time. However, much of the evidence on Earth has disappeared due to erosion and plate movement. The moon preserves this record more clearly. The South Pole Aitken Basin stands as one of the largest surviving examples of those ancient events. Another interesting feature of the basin is its influence on nearby terrain. The impact that formed it released enormous energy into the surrounding crust. Shock waves spread outward through the rock, altering areas far from the center of the collision. These waves fractured the crust and may have changed how later impacts shaped the surface nearby. Large sections of the far side show signs of this early disturbance. Some crater patterns appear slightly stretched or broken where the crust was weakened long ago. The basin may also have influenced the movement of molten rock inside the moon. When such a massive impact occurs, it can change how heat flows through the crust and mantle. Some researchers suggest that the basin forming collision altered the internal structure of the moon in that region. Even billions of years later, the effects of that event may still influence the geology of the surrounding area. The surface within the basin also shows a mixture of different rock types. Some regions appear darker than the nearby highlands. These darker areas suggest that limited volcanic activity may have occurred there after the main impact. However, these volcanic deposits cover only small sections of the basin compared with the Maria on the near side. Most of the basin floor remains rough and heavily cratered. Sunlight moving across this terrain reveals ridges, slopes, and scattered peaks left from earlier impacts. Because the basin lies near the lunar South Pole, parts of its interior experience long periods of shadow. The angle of sunlight in this region remains low for much of the lunar year. Some deep craters inside the basin may remain in shadow almost all the time. These permanently shadowed areas can remain extremely cold. Temperatures there can drop far below those found in most other parts of the moon. Such cold regions are of interest because they may trap small amounts of ice delivered by comets or other icy bodies. If ice exists there, it could provide useful resources for future lunar missions. For now, most study of the basin comes from orbiting spacecraft that observe its surface from above. High-resolution cameras continue to reveal small features across the terrain. Each new map adds detail to the understanding of how the basin formed and how it changed over time. The South Pole Aitken Basin therefore holds several important clues. It records one of the largest impact events known in the solar system. It may expose rock from deep inside the moon, and it preserves some part of the ancient history of collisions that shaped many worlds long ago. For these reasons, scientists consider it one of the most valuable regions on the moon for future research. Its scale alone makes it a central feature of the far side landscape. The basin stands as a reminder of how powerful early impacts were and how strongly they shaped the surfaces of planets and moons across the solar system. Conditions on the far side of the moon are shaped by the same basic forces that affect the near side. The moon has almost no atmosphere. Without a layer of air, heat does not move across the surface in the way it does on Earth. Each place on the moon warms and cools, mainly through direct sunlight. When sunlight reaches the surface, the ground begins to heat. When darkness arrives, that heat escapes into space. This creates large changes in temperature. During the lunar day, surface temperatures can rise to about 120 degrees Celsius in areas that face the sun directly. When night arrives, the ground cools rapidly. Temperatures can fall to around minus 170 degrees Celsius. These changes happen slowly because a single lunar day lasts about 29 Earth days from sunrise to sunrise. Sunlight moves across the landscape at a slow pace, giving the surface many hours to warm. Once the sun sets, the long night begins. During this period, the ground continues to lose heat for many days. Without air to hold warmth, the surface becomes extremely cold before sunrise returns. The far side experiences the same pattern. Half of the time it faces the sun, and half of the time it faces deep space. Because of tidal locking, the far side never faces Earth. But this does not affect how sunlight reaches the ground. The cycle of day and night remains the same across the entire moon. However, the terrain on the far side creates many local differences in temperature. Craters, ridges, and slopes affect how sunlight reaches the ground. When the sun is low above the horizon, crater walls can cast long shadows across the floor below. These shadows may last for many hours or even days during the slow passage of sunlight. Inside deep craters near the lunar poles, sunlight may never reach the bottom at all. The angle of the sun in those regions remains very low throughout the year. Some crater floors remain in shadow for extremely long periods. Because sunlight rarely enters these areas, temperatures stay very cold. In some places, they may remain below minus 200 degrees Celsius. These permanently shadowed areas can act as traps for small amounts of ice. If water molecules arrive there from comets or other sources, the cold environment can keep them frozen for long periods. Although the far side contains many craters, most of the surface still experiences the normal cycle of sunlight and darkness. During daylight hours, the ground absorbs energy from the sun. Darker areas, such as small volcanic deposits, absorb more heat. Lighter highland rock reflects more sunlight and warms more slowly. These differences create small changes in surface temperature from one location to another. Another important factor on the moon is radiation. Because the moon has no thick atmosphere and no global magnetic field like Earth, its surface remains exposed to radiation from space. Particles from the sun travel outward through the solar system in a steady flow known as the solar wind. These particles include protons and electrons moving at high speed. When they reach the moon, they strike the surface directly. Some of the particles become trapped within the top layer of soil. Others bounce away into space. Over long periods, this steady flow slowly changes the outer layer of lunar material. Cosmic rays also reach the surface. These rays come from distant sources, such as exploding stars and other energetic events in the galaxy. They travel across space at very high energy levels. When they strike the lunar surface, they can break apart atoms in the soil and rock. This process creates small changes in the chemical makeup of the material. The far side receives the same radiation environment as the near side. Both hemispheres face space without protection from air or a magnetic shield. However, one difference does exist. The near side sometimes receives slight protection from Earth's magnetic field when the moon passes through it. This event occurs when the moon moves through the long magnetic tail that extends away from Earth on the side opposite the sun. During those times, the near side experiences a small reduction in direct solar wind exposure. The far side does not receive that same shielding. Because it faces away from Earth, it remains exposed to the full stream of solar particles during those periods. Even so, the overall effect across the moon remains similar for both hemispheres. Another constant process affecting the far side is the steady arrival of micrometeorites. Micrometeorites are very small pieces of rock and metal traveling through space. Many are no larger than grains of sand. Even at that small size, they move extremely fast. When they strike the lunar surface, they release energy and break apart small amounts of rock. These tiny impacts occur continuously. Over millions of years, they slowly grind the surface into finer particles. Larger rocks break down into smaller fragments, and dust spreads across the ground. This process creates a loose layer called regolith. Regolith covers almost the entire surface of the moon. It is made of crushed rock, dust, and small glass particles formed during impacts. On the far side, the regolith layer can reach several meters in thickness in some areas. In regions with many old craters, the layer may be even deeper. Each new impact mixes the soil and moves material from one place to another. The regolith is not smooth like sand on a beach. Instead, it contains sharp edges and rough fragments created when rock shatters during collisions. Because there is no wind or water to round these pieces, the particles remain jagged. This texture gives the surface a powdery but gritty character. When spacecraft land on the moon, their engines disturb the regolith and send clouds of dust into the airless environment. Without air resistance, the dust follows simple arcs before falling back to the ground. On the far side, the same loose soil covers the crater rims, slopes, and flat areas between impacts. Sunlight striking this dusty layer reflects strongly from the lighter minerals found in the highlands. From orbit, the far side often appears bright because of this reflective material. The regolith also holds small glass beads created during past impacts. When an object strikes the surface, the heat can melt tiny portions of rock. As the molten material cools quickly, it forms small droplets of glass. These droplets mix with dust and fragments in the soil. Over billions of years, this process has produced a complex mixture of materials within the lunar regolith. The surface layer therefore acts as a record of many different events. Fragments from older craters, pieces of distant impacts, and particles from the solar wind all become part of the soil. Even though the far side appears still and silent, these slow processes continue every day. Micrometeorites keep striking the ground. Radiation from space continues to interact with the surface. Sunlight warms the rock during the long day, and the cold of night removes that heat again. Together, these forces shape the uppermost layer of the moon, little by little. The landscape does not change quickly, but it never remains completely unchanged. Over long periods, even small effects leave visible marks. Fine dust settles across crater floors, rock fragments break apart, new tiny craters appear across the regolith. These constant changes form the environmental conditions that define the far side of the moon today. They explain why the surface appears dusty, rough, and heavily worn when seen through the cameras of orbiting spacecraft. Even without air, water, or active volcanoes, the moon continues to evolve through the steady influence of sunlight, radiation, and countless small impacts from space. For a long time, the far side of the moon remained a place that spacecraft could see only while passing overhead. Orbiters mapped the terrain and sent images back to Earth, but landing there created a new problem. The far side never faces Earth. Because of this, a spacecraft sitting on that surface cannot send a direct radio signal home. Radio waves travel in straight lines through space. When the moon stands between the lander and Earth, the signal cannot pass through the solid body of the moon. It becomes blocked. For many years, this simple problem prevented direct exploration of the far side surface. Early lunar landings, including those carried out by the United States and the Soviet Union, all took place on the near side. That hemisphere always faces Earth, which allows constant radio contact. Engineers could guide the spacecraft, receive data, and control experiments. The far side required a different approach. The solution involved placing a relay satellite in space above the moon. A relay satellite acts as a communication bridge. It receives signals from one location and sends them onward to another. In this case, the relay satellite would listen to the lander on the far side. It would then send the message back toward Earth. China developed such a system for a mission known as Chang'e 4. Before the lander could travel to the moon, a separate spacecraft was launched to serve as the relay station. This satellite was named Queqiao. The name comes from an ancient story and means magpie bridge, a symbol of connection. Queqiao was launched in 2018 and placed into a special orbit around a point in space known as the Earth-Moon L2 point. This point lies about 65,000 kilometers beyond the moon on the far side relative to Earth. At this location, the combined pull of Earth and the moon allows a spacecraft to remain in a stable position with small adjustments. From that position, Queqiao can see both Earth and the far side of the moon at the same time. That clear line of sight allows it to receive signals from a lander on the far side and relay them back to Earth. With the communication system in place, the Chang'e 4 spacecraft began its journey. The mission launched from Earth in December 2018. After traveling through space and entering lunar orbit, the spacecraft prepared for its descent toward the far side surface. The landing site was chosen inside the South Pole Aitken Basin, one of the oldest and largest structures on the Moon. Specifically, the lander targeted a region known as Von Karman Crater. This area lies within the larger basin and offers relatively flat terrain for a safe landing. On January 3rd, 2019, the Chang'e 4 lander descended toward the surface. Guided by onboard systems and data from orbit, the spacecraft slowed its fall using rocket engines. Cameras scanned the ground below to detect hazards such as large rocks or steep slopes. As the lander approached the surface, its engines reduced speed further. Finally, the spacecraft touched down on the far side of the Moon. It became the first mission in history to land there successfully. Once on the ground, Chang'e 4 began sending signals upward to the Queqiao relay satellite. The satellite then transmitted those signals across the distance back to Earth. This system allowed engineers to receive images, measurements, and status reports from the lander. Along with the lander, the mission carried a small rover named U-22. After landing, a ramp opened and the rover slowly rolled onto the surface. U-22 began exploring the nearby terrain, moving across the dusty ground of the crater floor. The rover travels slowly to avoid hazards. Its wheels are designed to move across loose regolith and small rocks. Cameras mounted on the rover provide detailed views of the surrounding area. As U-22 moves, it sends images and scientific data back through the lander. The lander then forwards this information to the Queqiao satellite, which relays it to Earth. This chain of communication allows continuous contact despite the Moon blocking a direct signal. The instruments carried by Chang'e 4 study several aspects of the far side environment. Cameras record the shape and texture of the ground. Spectrometers measure the light reflected from the soil and rocks. These measurements help scientists learn about the chemical makeup of the surface. Ground-penetrating radar on the rover sends radio waves into the soil. By measuring how the waves bounce back, scientists can estimate the layers beneath the surface. This method reveals how the regolith formed and how thick it may be in that region. Another instrument studies the interaction between solar radiation and the lunar surface. Because the far side receives direct exposure to space, it provides a useful place to observe how solar particles affect the soil. The mission also carried a small sealed experiment to study how living organisms respond to lunar conditions. Inside this container were seeds and other simple life forms. The experiment aimed to observe how they might grow under controlled conditions in the Moon's low gravity. While the main focus of the mission remained geological study, the experiment showed that the far side could support controlled biological tests inside sealed systems. Chang'e 4 continues to operate long after its landing. Each lunar day, the rover wakes as sunlight reaches its solar panels. It travels short distances and performs new measurements. During the long lunar night, the rover enters a low-power state to survive the cold temperatures. Data from the mission continues to improve maps of the far side terrain. The landing inside the South Pole Aitken Basin allows scientists to examine rocks that may come from deeper layers of the Moon. Images from U-2 reveal a landscape filled with small craters, scattered rocks, and fine dust. These views match what orbiting spacecraft had already suggested. The far side surface remains rough and heavily shaped by impacts. The success of Chang'e 4 proved that long-term exploration of the far side is possible. The relay satellite system solved the communication problem that once limited missions to the near side. With that obstacle removed, its future spacecraft may explore many more locations across the hidden hemisphere. Plans for new robotic missions already include additional landers, rovers, and sample return projects. Some proposals even consider building radio telescopes on the far side. Because the Moon blocks radio signals from Earth, The far side offers an unusually quiet place for certain types of astronomical observation. For now, the Chang'e 4 mission stands as the first step in this new stage of exploration. A region that remained hidden for thousands of years now hosts working machines that travel across its surface, sending information back through space. Through this chain of technology, lander, relay satellite, and ground station, scientists continue to study the far side of the moon in detail. The far side of the moon offers a unique environment for observing the universe. Unlike the near side, it is shielded from most radio signals generated on Earth. Cities, satellites, and communication systems all produce electromagnetic waves that travel through space. These signals can interfere with sensitive instruments trying to detect faint radio emissions from distant stars, galaxies, and other cosmic sources. On the near side, this background noise makes some types of observations difficult or impossible. The far side, by contrast, remains naturally quiet. Its permanent orientation away from Earth blocks the majority of terrestrial radio transmissions. Scientists refer to this as radio silence. Because of this shielding, a telescope placed there can detect faint signals without interference from human technology. This advantage makes the far side a prime location for certain kinds of astronomical study. One type of observation that benefits from this environment is low frequency radio astronomy. Radio waves at very low frequencies cannot penetrate Earth's ionosphere. Ground based instruments cannot detect them effectively. Space based instruments face challenges due to interference and limited coverage. On the far side, however, low frequency waves can reach a telescope without obstruction. These signals carry information about the earliest stages of the universe, including the formation of the first stars and galaxies. Observing them could provide new insights into cosmic history that are otherwise inaccessible. In addition to radio silence, the far side offers protection from direct human influence. The moon does not have an atmosphere to scatter light or signals. It is free from the constant artificial noise that surrounds Earth. Spacecraft orbiting or landing on the near side still experience occasional interference from communication networks or other human activity. On the far side, such interference is nearly absent. This allows instruments to operate under more controlled conditions, improving the quality and reliability of measurements. Another benefit comes from the lack of nearby bright light sources. Telescopes on Earth must contend with daylight, city lights, and other optical interference. Even in space, orbiting telescopes often pass over illuminated areas of Earth or other satellites, producing brief periods of glare or noise. On the far side, a telescope can remain in shadow from the sun or face a clear sky for extended periods. This stability allows long observation sessions and the accumulation of data over time without interruption. Plans for far side telescopes consider both radio and optical instruments. Radio telescopes take advantage of the natural shielding, while optical telescopes could use remote or orbital support to observe specific wavelengths. Some concepts involve deploying arrays of small antennas across the lunar surface. These arrays would work together to form a single, large telescope. By combining signals from multiple points, scientists can achieve higher resolution and detect finer details in distant cosmic objects. The far side's stable surface provides a foundation for such arrays with minimal vibration or environmental disturbance. The South Pole Aitken Basin offers particularly interesting locations for telescope placement. Its large, flat areas could host arrays of instruments. Deep craters near the poles can serve as natural basins for telescopes, providing both stability and protection from stray radiation. In addition, these locations remain in shadow for long periods, which is useful for some types of sensitive equipment that must avoid heating from direct sunlight. Building telescopes on the far side also addresses challenges of long-term stability. Instruments on Earth must endure weather, wind, and seismic activity. Space telescopes in orbit face microgravity and orbital debris. On the moon, the surface is solid and stable. Gravity is low but consistent. There's no weather to erode structures or disturb instruments. This allows telescopes to remain fixed in precise positions for years, supporting long duration observations. Communication remains a key factor, just as the Chang'e 4 mission relied on the Queqiao relay satellite. Future telescopes would need systems to send data back to Earth. Relay satellites positioned beyond the far side could provide continuous communication. Data collected by instruments could travel through these satellites, maintaining a flow of information without interruption. This combination of stable surface, natural shielding, and reliable communication makes the far side one of the most promising locations in the solar system for next generation astronomical observatories. In addition to studying the early universe, far sighted telescopes could observe phenomena that are difficult to detect elsewhere. For example, pulsars, black holes, and interstellar plasma all emit radio waves that are often faint and scattered by human made interference near Earth. The moon's far side allows a cleaner signal, improving the ability to measure these sources accurately. Over time, networks of instruments could monitor multiple regions of space simultaneously, creating a global scale observatory isolated from terrestrial noise. Scientists also consider the far side valuable for testing technology. Building and operating telescopes in such a remote location requires solutions for energy, thermal control, and maintenance in low gravity and extreme temperatures. Developing these systems on the moon would prepare for future observatories on other planets or in deep space. Experience gained from far side operations can inform designs for long term missions where human presence may be limited or absent. Furthermore, the far side can act as a benchmark for observing subtle phenomena. Signals that might be distorted near Earth can be studied in their natural form. By comparing data collected on the far side with measurements from Earth and orbital telescopes, researchers can identify the effects of interference and improve models of signal propagation. This cross comparison enhances the accuracy of astrophysical measurements and expands scientific understanding. Another advantage of the lunar far side is the long periods of observation it allows. Because the moon rotates slowly, a telescope can remain pointed at a target for days without interruption from daylight cycles or atmospheric changes. This is particularly useful for observing slow or faint events, such as gradual changes in distant galaxies or transient radio bursts. On Earth, such observations are often limited by time zones, weather, and day night cycles. On the moon, instruments benefit from stable conditions that permit uninterrupted data collection. Future plans also include coordinated arrays of telescopes placed in multiple regions across the far side. By combining their signals, scientists could create a larger effective aperture, increasing sensitivity and resolution. This approach mimics methods used on Earth in radio astronomy, such as very long baseline interferometry. On the moon, the absence of interference enhances the quality of these combined observations, making the far side an ideal platform for expanding the scale of astronomical study. The far side of the moon provides a naturally quiet and stable environment for telescopes. Radio silence from Earth shields instruments from interference. The stable surface supports precise placement of antennas and optical devices. Extended periods of observation without day-night interruptions allow long-duration monitoring. Together, these advantages create unique possibilities for studying the universe in ways not possible from Earth or near Earth orbit. As technology continues to advance, the far side may become a central location for future astronomical research, revealing details about the cosmos that have remained hidden until now. The far side of the moon holds a record of events from the earliest days of the solar system. Unlike Earth, where erosion, plate tectonics, and weather erase many ancient features, the moon preserves its surface almost unchanged for billions of years. By studying the far side, Scientists can observe the traces of early planetary formation and the heavy bombardment that shaped many worlds. The craters that cover the far side provide direct evidence of these early impacts. Each crater marks the location where an asteroid or comet struck the lunar surface. The size, shape, and distribution of craters reveal the frequency and scale of collisions that occurred long ago. Large basins, such as the South Pole Aitken, record particularly energetic events. These impacts were powerful enough to remove portions of the crust, exposing deeper rock layers. By examining these structures, scientists learn about the intensity of the environment in which the moon formed. The contrast between the near side and far side also offers clues. The near side contains broad, dark plains of basalt, while the far side is heavily cratered and lacks extensive maria. This difference indicates that the moon's crust was not uniform in thickness and composition. Early in its history, molten rock erupted more readily on the thinner near side. On the far side, the thicker crust limited volcanic activity. Understanding these variations helps scientists model how the moon cooled and how internal heat moved within its interior. These insights apply not only to the moon, but to other planetary bodies that formed in similar conditions. Studying rocks from the far side also provides information about chemical processes in the early solar system. Impact events mixed surface materials and occasionally brought mantle rock to the top. Analyzing the composition of these rocks allows researchers to trace the distribution of elements during planetary differentiation. The ratios of specific minerals reveal how heat and pressure shaped the moon's interior, and by extension, how other rocky bodies may have evolved. The far side's surface also preserves evidence of small impacts from comets and asteroids that occurred after the moon had cooled. These secondary impacts help scientists understand how debris in the solar system changed over time. By counting and dating these craters, researchers can estimate the intensity of late heavy bombardment, a period when many planets and moons experienced frequent collisions. This information provides context for the formation of Earth's surface and early conditions for life. Additionally, the far side offers insights into the stability of planetary surfaces over long periods. The lack of atmosphere and water means that craters and geological features remain intact for billions of years. By comparing regions of different ages, scientists can see how the lunar surface evolved under constant exposure to sunlight, radiation, and micro impacts. This record is a unique laboratory for understanding planetary aging and surface processes in the absence of erosion. Data from robotic missions, such as Chang'e 4, have expanded knowledge about regolith formation. The soil on the far side contains fragments from ancient impacts, as well as material altered by radiation from the sun. These layers reveal a chronological record of surface conditions. Scientists can distinguish older deposits from more recent ones, giving insight into the timeline of events that shaped the lunar crust. By extension, this helps reconstruct the early history of Earth's own surface, which has been largely recycled by geological activity. The study of far-side craters also informs theories about impact mechanics. Researchers analyze the size, depth, and morphology of craters to estimate the energy released during collisions. This information is important for understanding how planets acquire mass and how impacts influence planetary evolution. Large collisions can redistribute material, form basins, and even trigger volcanic activity. By examining these effects on the moon, scientists develop models applicable to early Earth, Mars, and other rocky planets. The chemical composition of rocks from the far side offers another layer of information. The presence of specific elements, such as titanium, iron, and magnesium, can indicate the conditions under which the rock formed. Variations in composition across different regions reveal how the lunar mantle and crust differentiated over time. These differences also help explain why the far side lacks extensive maria. By studying mineral distributions, researchers gain insight into the processes that governed the moon's early development. Remote sensing instruments provide additional clues about the early solar system. Spectrometers measure the light reflected from lunar rocks and soil, revealing mineral content. Radar instruments probe below the surface, identifying layers of regolith and fractured rock. Thermal measurements show how heat moves through the crust. Together, these data sets allow scientists to reconstruct the moon's geological history with increasing precision. Understanding the far side also informs planetary formation theories. The moon likely formed from a giant impact between Earth and a large protoplanet. Studying the composition and structure of far side rocks provides constraints on models of this event. Variations in crust thickness, mantle exposure, and elemental ratios can confirm or challenge theories about how material from both bodies mixed during the collision. In this way, the moon serves as a record of processes that shaped not only itself, but also the early Earth. The far side also preserves evidence of solar system evolution beyond local impacts. Micrometeorites, cosmic rays, and solar wind particles have interacted with the surface over billions of years. By examining how these external factors altered the soil, scientists can track changes in the space environment. This includes variations in radiation intensity, the arrival of cometary material, and shifts in the solar wind. Such data help reconstruct conditions in the inner solar system during the moon's early history. Finally, studying the far side improves understanding of comparative planetology. By observing the differences and similarities between the near and far sides, researchers can apply these findings to other celestial bodies. Features like basins, crater densities, and regolith thickness offer insights into impact frequency, volcanic activity, and thermal evolution. These observations contribute to a broader understanding of how rocky planets form and change over time. In summary, the far side of the moon acts as a natural archive. It preserves the history of impacts, volcanic processes, and surface evolution. By studying this hemisphere, scientists gain insight into planetary formation, the intensity of early solar system bombardment, and the development of Earth's satellite. The information collected allows researchers to reconstruct a detailed timeline of events, offering a window into the conditions that existed during the first billion years of the moon and the inner solar system. Each crater, ridge, and regolith layer contributes to this story, revealing patterns that cannot be observed elsewhere. As robotic missions continue to explore and measure the far side, the moon's hidden hemisphere provides ever more precise knowledge about the early solar system and the processes that shaped terrestrial planets. Looking at the far side of the moon reveals not only its past, but also its potential for future study. The combination of stable ground, preserved ancient features, and natural shielding from Earth's interference makes this hemisphere uniquely valuable. Scientists continue to plan missions that will expand knowledge of its geology, chemistry, and environmental conditions. Robotic landers, rovers, and relay satellites create the foundation for long-term research. These systems can collect continuous data over years, providing insight into processes that unfold slowly in the moon's extreme environment. Future missions may include more advanced telescopes, instruments for sample collection, and experiments to test new technologies for lunar habitation. The far side's regolith, craters, and basins will remain a record of billions of years of solar system history. Each new measurement, whether of surface composition, impact patterns, or radiation levels, adds to the understanding of how rocky planets evolve. By combining observations from the far side with data from the near side and orbiting spacecraft, researchers build a complete picture of the moon's structure and history. In addition, the far side serves as a testing ground for tools and methods that may one day be used on other worlds. Lessons learned from communication, energy management, and instrument deployment inform the design of missions to Mars, asteroids, and beyond. The moon becomes not only an object of study, but also a platform for exploration and technological development. As science advances, the far side of the moon remains a place of discovery. Its surface continues to tell the story of impacts, volcanic activity, and interactions with the space environment. With each mission, more details emerge, revealing patterns and processes that are impossible to study elsewhere. Over time, these findings will deepen understanding of the Moon, the Earth, and in the wider solar system, establishing the far side as a key location for future research and observation.